Okay, so we're going to be talking about chemical bonds. So there are three types of chemical bonds that we have. One of them is called ionic. One is called covalent. And one is called metallic. Okay, so ionic is composed of ions, right? We've talked about ions. What are ions? Charged particles. And what do I mean by that? Charge. That's right. Okay, so they're either negative or positive, right? Now we're talking about these molecules being wholly charged, right? So they're going to have plus, one, minus. Okay. So if it's a positively charged ion, it's called a cation. Okay. I'm blaming Russia for this. Yeah, watch it. Is it gonna work? Oh my gosh. Okay, so let me switch. Oh, I spoke too soon. That's right. Damn Russia. Okay. Okay, so cation positively charged, anion negatively charged, right? You got a quick picture of it? Yeah. Okay. It's not working here and on the, yeah. So, and it was working fine earlier, it just decided, okay, we're going to stop right now. You think it's going to be easy? It's not the first time. Because it hears me, I want to throw it out the window. That's what it is. Okay. So, yep. Okay, so, and then an anion is a negatively charged, right?
I know it just keeps getting worse.
Hey now. Okay, so let's say we have sodium. We know that sodium has how many valence electrons? Valence electrons. One. Sodium is in group one. All group one metals have one valence electrons. Valence electrons are what? You know this. It's outer shell. Okay, so that's true. Outer shell. What else? Okay, what are they for? They're used for bonding, right? So we're going to be able to use them either to give away, to add on to, right? So when we drew the Lewis structure of sodium, it has a single dot. Okay? Because it has one valence electron. It can get rid of one electron. Chlorine. Chlorine has how many valence electrons? It's in group 17, right? It's technically one away from being a noble gas. So if you're a noble gas, you have 8 electrons surrounding you. So if you're one away from being a noble gas, how many electrons must you have around? 7. So you have 7 dots around chlorine. So sodium has 1 to give away. So it's going to give away its electron to chlorine. So then sodium becomes what? It lost an electron. You have to be patient. Sodium, if it's lost an electron, it's gonna happen. What was that? I heard somebody said positive. It becomes a cation, right? So it has a positive charge. So when you're doing the Lewis structure, we're going to put a plus here to let us know that we've lost one electron, right? We lost one dot in the case of the Lewis structure. Where chlorine is gaining one, right? Because sodium is donating that one electron to chlorine. So then chlorine have 8 electrons around it. And since it gained one electron, what's going to be its charge? Negative. Okay. So if I have a positive and a negative, what happens? It attracts. And we form an ionic bond. And we get sodium chloride. Okay. So if we looked at P table, see if my other programs work. So test everything out. We're going to see how much we can break in a day. Can you guys see P table? So if we look at P table, and we have that sodium. Sodium lost one electron, right? So since sodium lost one electron, how many electrons would sodium have? How many? So it would have lost one valence electron, then it would have 0. But how many electrons does sodium have normally? 11. So if I lose one, it has 10. So who else has 10 electrons? Neon. Okay. So sodium becomes like neon in terms of the number of electrons, right? So this process, the fact that sodium wants to be like the noble gases, everybody wants to be like the noble gases in terms of the number of electrons. Because the noble gases are wealthy. They have everything that they could possibly need. Their outer shell is full. So your goal is to try to be like the noble gases. So sodium gets that by losing that one electron, right? So we would say that sodium ion, Na plus, and neon are isoelectronic. Iso meaning same, electronic, number of electrons. Isoelectronic. So I'll type that out because my handwriting is a third grader. Okay. But then you have to deal with my spelling. See, so it's catch-22. Okay, so isoelectronic basically means the same number of electrons. Okay. So chlorine ion, where's chlorine? What is the atomic number for chlorine? 17. So if chlorine gains 1 electron, like it did, it's going to be isoelectronic to who? Argon. Okay. So let's look at nitrogen. Nitrogen is how far from being a noble gas? It's about 3, right? So 1, 2, 3, 3 away. So if nitrogen gains 3 electrons, how many electrons will nitrogen have? 10. So who would it be isoelectronic to? Neon. Okay. So the elements that are in the main group are trying to be like the noble gases. So main group meaning group 1, 2, group 13 to 18. That's your main group. So everybody wants to be like the Johnsons. Everybody wants to be like the noble gases because they're wealthy. Okay. Okay. So ionic bonds is just that giving and the taking of electrons so that you can be like the noble gases. Okay. Now, when we really look at ionic compounds, see if I can get it to work again. I'm going to try. You guys are gamblers, right? Gamblers. Okay, we're going to share. We're going to see if it works. See if I get an image up real quick, and then before it crashes again. It's going to be a long lecture, isn't it? Okay, so here, the ones that are in green are also all isoelectronic to helium. And I know you guys can't see it. The ones that are in blue are all isoelectronic to neon. The ones that are in yellow are all isoelectronic to argon. The ones that are in pink, all isoelectronic to krypton. And the ones that are in orange are all isoelectronic to xenon. Okay. So those ions, their goal are trying to be like the noble gases, right? So ionic bonds are always going to be formed between metals and nonmetals. Yeah. What was that? I said ionic bonds are always formed between metals and nonmetals. Metals, I go to my P table since things crashing again. Metals. So metals and nonmetals. So ionic bonds. Okay. So metals are always going to be the cations. The nonmetals are always going to be the anions. Okay. So let me write that down. Metals are cations. Okay, so metals are going to form cations and nonmetals anions. That's right. Okay, so it doesn't want to work today. Okay. We know that from nomenclature, they have to balance out. At the end of the day, it has to be a total of a neutral charge. So electrostatically, it has to add up to 0. So my positive charges have to add up to my negative charges. Okay, so we know if we had aluminum, aluminum has what charge associated with it when it forms an ion? That's right, a 3+ charge. And oxygen, when it forms an ion, has what charge associated with it? Okay. So I know that I'm going to need how many aluminums to balance out how many oxygens? Okay. I'm going to need 2 aluminums to balance out 3 oxygens. And then I know that since this is an ionic compound, when I name it, I'm going to call it aluminum oxide. Okay. Because I always know that aluminum is always going to be what charge when it forms an ion? +3. That's right. And then I know that oxygen is always going to be -2. Okay. Unless it's special. Talk about that later. There's always exceptions, you know? Okay. So now the thing about this is these ions, the way that they kind of form, it's kind of like they form what we call a lattice, a crystal lattice. So the positive charge will be next to the negative charge, will be next to the positive charge, will be next to the negative charge. So like in the case of sodium chloride, it's going to look like this. So this will be sodium. Yeah, let me instead of trying to draw it out. The greens are going to be sodium. Okay. Now nothing's working today. It's old school. Okay, and we know that the sodium has a plus charge, and the browns are going to be chlorine. So you're going to have alternating between the sodium and the chlorine and the sodium and the chlorine and the sodium and the chlorine and the sodium and the chlorine. That's what's going to form your crystal lattice. Okay. Yeah. I'm going to see if I can pump it up real quick before it crashes. Actually, let's see if I can do it like this. We won't even get started. It looks like that.
Oh, wow. Let's not do that again.
Hey now, the only thing is 3-dimensional. Hey, it's the best. It's the same thing. It's alternating. It's alternating, right? You see the alternating? Let me show you. You'll see it when I put it up there, right? So hold on. It's working. Hey, I should probably let borrow your computer then. Oh, okay. So this here represents the three-dimensional, right? So it's alternating. Sodium, chlorine, sodium, chlorine, sodium, chlorine. So you're getting an alternating lattice, but it's a three-dimensional lattice, right? So in other words, they're going to be surrounded by the positive charges, right? Negative charges surrounded by positive. And so you're going to get a nice lattice formation, okay? So things that we know about ionic compounds. Ionic compounds, when they're melted, they loosen up those positive and negative charges. So that means that they're able to conduct electricity. So that positive charge can interact with that negative charge. Electrons are electricity are electrons that are moving, right? So you're just introducing electrons. And so you're able to get that shift between positive and positive and negative through that solution. So it conducts electricity, right? When we put it in water, it also conducts electricity because water separates those two, right? The positive and negative. You know that water was the home wrecker. Hey, baby, you don't need him, right? Remember that, right? So characteristics. So characteristics of ionic compounds. At room temperature, most of them are going to be solids. They're going to be strong, right? So the bond is relatively strong. And then they conduct electricity well when they're in solution, such as water, right? Or when they're melted. Okay. Now, covalent bonds. Can you guys see this at home? Ozzy, are you guys good? Okay. Okay, so covalent bonds are basically when we have two or more atoms sharing electrons. Okay, so electrons are going to be shared. We've talked about this at the very beginning. You guys remember me telling you about my sisters and the Atari, right? That's sharing, right? So we have two forms of sharing. We could have even sharing or uneven sharing. Even sharing means that the electron is being shared half the time here, half the time there, half the time here, half the time there, half the time here, half the time there. Gotta make sure they can see. There we go. Half the time here, half the time there. Okay, so uneven sharing means that, like I did with my sisters, I get it 90% of the time. My sisters get it 10% of the time. It's sharing, right? But it's just uneven, okay? So covalent bonds have those two possibilities. So when it's sharing evenly, that's called nonpolar. Nonpolar covalent. Bond. Okay. Or it's called a pure covalent bond. And that's sharing evenly. Okay. It's called polar covalent bonds. When sharing unevenly. Okay. Simple, right? So let me give you an example. Water. Water, this line here represents 2 electrons being shared between hydrogen and oxygen. This line here represents 2 electrons being shared between hydrogen and oxygen. These electrons here, these dots, this is a Lewis dot structure, again, for the compound. Water shares unevenly. Now, that basically means that the electron is spending more time around the oxygen than it is spinning around the hydrogen, the shared electron. That's right, that would be polar covalent because it forms 2 poles, a positive pole and a negative pole. Draw that here in a second. Let me put this line here. So this just lets us know where it starts from. The electron starts between the 2 and it goes towards the oxygen, right? So that means that the oxygen is going to have a greater electron cloud around it because the electron is spending more time around the oxygen than it's spinning around the hydrogen. Okay, now it's going to be considered to be what we call partially positive, this hydrogen. This here is the Greek symbol for delta, plus. So it's partially positive, meaning it's not a complete charge. It's like a fraction of a charge, right? So you're not like in the case of sodium and chlorine, where sodium gives up its electron completely. No, they're sharing the electron. It has it 10% of the time, right? But it's still getting that electron some of the time. And then the oxygen is going to be partially negative. So it forms 2 poles, a positive pole and a negative pole. Okay? You guys get that? Okay. So when we talk about molecular compounds, we're really making reference to compounds that are sharing electrons. So we're talking about covalent bonds. Okay. So here we have the Lewis structure or the Lewis symbol for hydrogen. Hydrogen has 1 valence electron. Okay. Now, both of these hydrogens, they want to be like neon. Neon is the nearest noble gas. So they need to have 2 electrons around them. This is the thing about hydrogen. Hydrogen only wants to have 2 electrons. Its octet, meaning 8, is really 2 because it wants to be like helium. Okay, so hydrogen wants to be like helium in terms of electrons. Okay, it needs to get 2 electrons around it, only 2. Okay, so in this case, it takes these 2 electrons and it shares them, and it forms a bond. This represents a bond. This line represents the sharing of 2 electrons. Now, a bond is only the sharing of 2 electrons, right? 1 bond is the sharing of 2 electrons. Sometimes we have to share more than 2 electrons, right? So here's oxygen. We know that oxygen is a diatomic. It forms a molecule. So oxygen wants to be like who? On your periodic table? I heard it. Neon. So since oxygen is trying to be like neon in terms of electrons, it needs to have 8 around it. So it's going to want to share more electrons. So there's 2, 4, 6 valence electrons around oxygen. This one also has 2, 4, 6 valence electrons around it. So in this case, I'm going to write this up here so you guys can write it down here. You won't be able to see it. So we have to rearrange the electrons So they're sharing for electrons. So that's 2, that's 4, that's 6, that's 8. That's 2, that's 4, that's 6, that's 8. So in this case, oxygen forms because we can only have 2 electrons in an orbital. Oxygen forms what we call a double bond. Okay, there's a lot of questions. I see it in your faces. Yes. There are going to be others. It all just depends because remember, the goal is so that you have 8 electrons around you, right? So the way I have 8 around me, oxygen has 6 valence electrons total, both of them. So it needs to come up with 2 more, right? So the way it does that is by these electrons are moving. Electrons are always moving, right? So in this case, there's those set of electrons are circling both of those oxygens. Yes, but they're sharing. So this guy's coming over here, it's coming over here. So sometimes this guy's at 8, sometimes this guy's at 8. So, but it's both of them are 8 because it's being shared. Does that make sense? No, it's not an exception. It's like this. Okay, you live in a house, right? You have a husband or a boyfriend, or you have a significant other, right? Doesn't he live in the same house as you? Do you guys share the house? So you both have the house, even though you're there some of the time and he's there some of the time, right? So, but you guys still share the house. And you still both have a place to live, right? Okay. So you're not sleeping on the floor when he's in the house, right? So that's the same thing with the electrons. The electron is constantly, it's moving so fast, but it's being shared between the two. So it's like it really has the electron, right? Okay, so you got to remember, it's not a static thing, it's a constant move, right? So it's literally orbiting around both of them. It's going, so it's really like they have. Yeah, but you would never notice it because it's so fast, right? And so since it is orbiting around it, so it's making like this little haze around it because it's always moving, right? So the electrons, even the ones that are around it, right, that are dedicated to it, these guys are called lone pairs. Those guys are dedicated to that atom. Even those guys are moving, right? But they're moving just around that oxygen, where the other one is moving around both sets, right? Does that make sense? You had a question. That's a good question. You're asking the right questions. So the way that we will be determining polar or non-polar is by the pole, right? Who's going to want the electron more, right? And so typically the closer you are to being a noble gas, the more your pull is going to be, right? So for instance, fluorine is 1 away, right? So fluorine is going to have a stronger pull than oxygen does. But since we have oxygen and oxygen, it's like twins, right? That are exactly the same size and neither of them are stronger than each other. So they're going to have equal pull. So if they have equal pull, then the sharing is going to be equal, right? So it's going to be nonpolar. That's right. Because nonpolar is equal sharing, right? Okay, so fluorine. Fluorine is also a diatomic element. Fluorine has how many valence electrons? So if we had F2, and we're going to draw the Lewis structure for fluorine, it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. One, 2, 3, 4, 5, 6, 7. Okay, so they both have 7 valence electrons. So for them to reach their octet, they're going to share how many electrons? 1. So they're going to form a bond here. If we count, that's 2, that's 4, that's 6, that's 8 around this fluorine. That's 2, that's 4, that's 6, that's 8 around that fluorine. Okay. So it's nonpolar because they're like twins, same pool. Okay. How are you guys feeling so far? Tired? That's all right. I'm right there with you. You see what's been happening to me all day long. This has been my problems. So this is nonpolar. That is correct. Yeah. Okay. What was that? Yes, I can do one that's polar. You're beating me to the punch. So let's say we have carbon and oxygen. Now, carbon and oxygen are located at different points of the periodic table, but on the same line. Let me show you. Carbon is here, oxygen is here. Okay, who is closer to being a noble gas? So who is going to want it more? Okay, so oxygen is going to have more pull. So how many valence electrons does carbon have? It has 4. 1, 2, 3, 4. How about oxygen? 1, 2, 3, 4, 5, 6. Okay, so now we need to shift this around so that we're sharing enough electrons that both of them reach their octet. There's a total of, you said 4 plus 6. So we have 10 electrons to work with. Now, they don't have to share, more. Sometimes the bigger guy has to give in more electrons to the pot. Sometimes the little guy has to give in more electrons to the pot. It just depends. But the goal is to shift them around so that you end up with 8 around both of them. But you have 10 electrons, okay, to work with. Okay, so how can I arrange this so that I end up with 8 around both? How many electrons should be shared between the two? Are you sure? You said 4 electrons? You said 3 electrons? Okay, so now we want to have 1, 2. Somebody said 4, right? We'll start off with 4, just for the hell of it. Kicks and giggles. So if we take these 2 and these 2 and put them in the middle, so that means that we have 1, 2, 3, 4. Okay, so then that's 2, that's 4, that's 6 around this carbon. Is that enough? No. So we know that this doesn't work, right? Let's draw a line through it. Let's draw a black X through it. Since we're not going to through it. Okay. So somebody said 3. Do you mean 6? Because so you're saying, yeah, that's right, because each line represents 2, right? So then that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. Okay, so that's 2, that's 4, that's 6, that's 8, that's 10. So we have what we call a triple bond, right? 3 lines, right? So that's 2, that's 4, that's 6, that's 8 around this carbon. That's 2, that's 4, that's 6, that's 8 around the oxygen. Both are happy, right? Triple bond, that's right. So this is called a triple bond because you're sharing 6 electrons. A bond represents 2 electrons being shared. Where fluorine was only sharing we're sharing 2 electrons, which makes 1 bond, right? So that's a single bond. Okay, and I showed you earlier where oxygen was sharing 4 electrons, and that was 2 bonds, so that's a double bond. What was that? That's right. Oxygen was a double bond. Okay, so carbon monoxide forms a triple bond so that it reaches this octet. Okay, how are you guys doing? Good, good. Okay, let's see if we can make it harder, right? Okay, let's see. What if I have N2? N2. So I want you guys to draw the little picture for that. How many valence electrons does nitrogen have? It has 5 valence electrons. Well, then you just draw 5 dots around it, right? That's how we started. 1, 2, 3, 4, 5. Right? You can do 3. We have flexibility. Remember, electrons are going to be moving. It does matter how they're shared because it has to be stable so that they both reach their octet, right? So we said it's 1 line. So let's do it if it's 1. The only way that we find out is by looking at it, right? So we have 1, 2, 3, 4, and then we have 1 line here. 1, 2, 3, 4, and that 1 line. So there's a total of 10 electrons that we're working with, right? So that's 2, 4, 6. Oh, that would only be 6 around nitrogen. Does that meet the octet? So we know that that one doesn't work. Okay, so if we did a double bond, so then that's okay, so that's 2, that's 4, that's 6, that's 8, that's 10, that's a total of 10 electrons, but that's 2, 4, 6, 2, 4, 6, 7 around nitrogen. Is that 8? No, so that doesn't work either. So that's 2, that's 4, 6, 8, 10. That's all 10 electrons. That's 2, 4, 6, 8 around nitrogen. 2, 4, 6, 8 around this nitrogen. That's 10. All right. So everybody's happy. 8 around it. They could have been on the top. Yeah. So that's 2, that's 4, because each line represents 2 electrons, right? Okay, so that's 2, 4, 6, 8 around this nitrogen. That's 2, 4, 6, 8 around this nitrogen. Okay. So is it polar? Is it polar or non-polar? It's non-polar. Why is it non-polar? They're sharing evenly, right? Yes. What was that? Oh, I thought you said you touched your brain. Yeah, I'm like, okay, man, that's a good thing. Hey, you know, hey. Okay. So we can actually do this with more than just 2 atoms. We could actually do it with 3 or 4 or 5, right? But the goal is to try to get it so that everybody has their octet full. So for instance, Can I erase? We've been looking at water, right? So let's actually break down water. Oxygen has how many valence electrons? It has 6 valence electrons. 1, 2, 3, 4, and I'm being lazy here. Okay, hydrogen has how many valence electrons? Hydrogen. It has 1. 1. Okay, so hydrogen wants to be like who? Helium. Helium has how many valence electrons? I mean, how many electrons around it? It has 2. So hydrogen is always going to want to have 2. So hydrogen will never, ever be in the center. Okay, so you will never have a molecule where hydrogen is in the center. It's always going to be at an end because it can never have, it can't have more than 2, right? If you have hydrogen in the middle, you have to have 4, right? That's 2, that's 4, right? Okay, so oxygen needs to have how many around it? 8, right? So that's 2, that's 4, that's 6, that's 8. Is this octet full? So it's good to go. Okay, where hydrogen only has 2, and that's what it wants, right? Okay, so what if I have NH3? What is this chemical called? Anybody remember? Ammonia. That is correct. It is called ammonia. So ammonia, who's going to be in the middle? Nitrogen is going to be in the middle. Why is nitrogen going to be in the middle? Because hydrogen can never be in the middle, right? So how many valence electrons does nitrogen have? 5. So it has 1, 2, 3, 4, 5. Okay. How many valence electrons does hydrogen have? 1. 1. Each one has 1, right? So if we form a bond here, a bond here, a bond here. So then that's 2 around this hydrogen, 2 around this hydrogen, 2 around this hydrogen, and then how many around our nitrogen? 8. Are we happy? Yes. Okay. Yes. Those are 3 single bonds. It's only triple bond when you're sharing a total of 6 electrons between 2 atoms. Good question, though. Very good question. Okay. You know, this is too easy. We got to make it a little more challenging. Okay. So let me introduce you to electronegativity. Let me see if I can get it to work. If I can, you know how things have been going so far. So. Did you say we're just guessing?
No.
Okay. So in the case of ammonia, these dots up here, these represent lone pair. Okay. So those are electrons that are not involved in bonding. Okay. So they're just surrounding that one atom. They're not involved in bonding. Okay. So again, you want to make sure that it obeys the octet rule. Now, there are going to be some exceptions, and we'll talk about those here in a minute. Okay. And there's my. We talked about polar and nonpolar. You guys are confident on that? You feeling good about it? So polar is that going to be even sharing or uneven sharing? Uneven sharing. Nonpolar, even sharing. Here's a beautiful picture of it that I couldn't draw. So this here is nonpolar. You have two identical, so the electron density of them is exactly the same. That reminds me to go back one. Here, the electron is spending more time around Y than it is X, so it has more of an electron density around it. So it's uneven sharing, that's right. And here, this is ionic bonding, where they're giving up the electron entirely. So there's no sharing of electrons. Okay, so ionic bonding, no sharing of electrons, you're either giving or you're taking, right? So,
I have to say, because it's still giving, right?
What was that?
Like if it's giving, it still has to stay together, right?
Yeah, it still stays together. Yeah, but it gives up one electron, right? Remember, there's still electrons around it, but it's giving up that one that was extra, like the one that's not safe for the bank, you know? Okay, so that's what that means. Good question, though. Really good question. Okay, so sharing is really an overlap of electrons. And so this is just showing you that the electron densities are overlapped and the electrons are literally orbiting both of them, right? In the case of the hydrogen, right? So both electrons are just constantly surrounding by both of them and are spending equal time on both sides, okay? So this is called overlapping orbits, right? That's what bonding essentially is. Okay, so the next thing I'm going to talk to you guys about is electronegativity. So, as I said, fluorine is one away from being a noble gas, so it's going to be more electronegative than oxygen. So, if we, I'm going to write this down now, 0.5. Okay, so with electronegativity, the way that you would actually do it, you can look at it, it'll give you a good idea. But in all honesty, electronegativity is just a pull of the electron. So the one that has the stronger pull wants the electron more, okay? So here, this is the table of the electronegativity. Fluorine has the strongest electronegativity. It has a 4.0. Oxygen has electronegativity of 3.4. So the way that we determine if it's going to be a polar bond, so this would be polar, nonpolar, and this would be ionic character. Okay. So if we take the difference between, let's say, a bond between oxygen and fluorine, fluorine is 4.0, so we take the number that's highest, and then you subtract the lower number. Oxygen is 3.4, and this equals 0.6. So if the number is between 0.5 and 1.8, it's polar. If it's less than or equal to 0.5, it's nonpolar. If it's greater than or equal to 1.8, it's ionic character. Okay, so here we have oxygen and fluorine. The value, the difference between the two is 0.6. Is that going to be polar or nonpolar? It's going to be polar, right? Because 0.6 falls between 0.5 and 1.8. Okay, so if I have carbon and hydrogen, a bond between carbon and hydrogen. Carbon is 2.6, hydrogen is 2.2. So 2.6 minus 2.2. And if my math is correct, is 0.4. No, you will get a table. You will get this. Once I'm able to print, you would have had it today if I was able to print. Right? So, but you'll get a full table of that, and you guys can use it on the exam. You can also get it from P-table as well. Your head is hurting. What's going on? No, ask the question. Here's an opportunity. You need to ask a question. Okay. Okay. So this here, these represent the desire for that atom to want electrons, right? Want electrons to pull them, okay? So you're calculating the pull, how strong they're going to be pulling the electrons when they're shared, okay? So fluorine has a value of 4.0, right? The reason I know that is because this table says fluorine 4.0, okay? So fluorine has the highest pull. It's small, it's strong, it's a bully. It pulls the electron. So if fluorine matches up with oxygen, if it forms a bond between oxygen and fluorine, meaning that they're going to be sharing electrons, oxygen and fluorine are going to be sharing electrons, then fluorine has a pull of 4.0 and oxygen has a pull of 3.4. So we take the difference between the two. If the difference is greater than 0.5, then it's polar, right? If the difference is less than 0.5, it's nonpolar, okay? If the difference is greater than 1.8, then it would be ionic character, meaning it's going to form an ionic bond, okay? So that means it's giving up the electron completely, okay? These are all bonds. That's right. Yep, that's what we're covering, exactly. So we're talking about bonds between them, right?
This is kind of like I don't know, whenever we were doing
Structure, yeah.
yeah, I was like, wait, I was trying to
Whether it's polar and where, yeah, exactly. So this tells us exactly if it's, so other than, so normally what we would do, we would rely on where it's located at. And then that would be it. That would be the closest we get. This gives us actual numbers to use. So you can say, okay, we're sure about this. This is definitely going to be a polar bond, or this is going to be a non-polar bond. You should do it this way because this is more exact. Yes. Yes, it is, because it's very defined, right? There's no, oh, well, what happens? What happens when I have chlorine and oxygen? Well, let's take a look what happens when we have chlorine and oxygen. Well, chlorine is 3.2, right? Oxygen is 3.4. right? So if I subtract those two, what is that going to be? 0.2. So it would be nonpolar. So the bond between oxygen and chlorine would be nonpolar. It's just a quick glance. You know? Okay. So that way we can tell the bond between those two is going to be nonpolar. Now, you've got to remember that we're talking about a bond between two atoms. It's not talking about the molecule as a whole. We're talking about the bond between two atoms. Start talking about the molecule as a whole in chapter 13, okay? Which we're not there yet. Okay, so let's say we have beryllium and fluorine, Be and F. Do you guys mind if I erase some of this stuff so that okay? So fluorine is, what is the value for fluorine? 4.0. And beryllium, it's 1.6. Okay, 1.6 minus 4.0 minus 1.6. Okay, so is that nonpolar, polar, or ionic character? Okay, that's it, right? Piece of cake, ionic character. Okay. Questions, concerns? Well, everybody wants the money. Okay. Pass the class. Get you closer to the money. No. Rhyming me. Yeah. So no, because usually what I do, and it'll happen again, don't worry about it. Like questions like this, something that I'm like, hey, we've gone over this, like nomenclature and stuff like that. I'll give you guys, okay, so what does this mean? Usually it's with sig figs. I usually make all my money during, because who was it I made a bet with? Oh, actually, it was David, I think, who isn't here right now. Made a bet with him, $5 for this, right? Yeah. No, I know. That's usually how I use my money. That's how I bet that money. That's the money I bet. At one point, I had about $20 in there. So, but students started getting better towards the end of the semester. So then I started losing money. So I'm like, okay, we can't put any more money out there. Okay, so we've already talked about it. So a single bond is sharing of one pair, which is a total of how many electrons? 2 electrons. Double bonds is sharing of 2 pair, which is a total of how many electrons? 4. Okay. A triple bond is the sharing of, okay. You guys are getting this, man. Piece of cake. So we've already talked about if you have more than more than 2 atoms. So in the case of water, we've already given that as an example. Here's what we've done with the nitrogen. Now, exceptions. Here's the fun part. There are a lot of exceptions. That's the problem. Is that, yeah. And exactly. But that's the best part. Yeah, the best part about science. Well, some of it is like what you're saying. Some of it is that we have hypotheses. We're not 100% sure on certain things, and some of it is. Yeah, so we put an exception on it. This is an exception because it doesn't obey those rules. We saw that we've done the experiment. It doesn't obey those rules. We can't quite explain it, but it doesn't obey those rules. Some of them we know why it does that, right? So this will be a reason why. Like for instance, The octet rule. So we want to try to obey the octet rule if we can obey the octet rule. But these are going to be exceptions to the octet rule. These are known exceptions to the octet rule. One exception is when we have an odd number of total valence electrons. So for instance, if we have nitrogen monoxide, nitrogen has how many valence electrons? It has 5. And oxygen has how many valence electrons? So regardless of how you try to put it around there, you have 11 valence electrons. Regardless of how you do it, you're never going to get to the point where you have 8 around both of them. One is always going to have 1 less than the octet. So the way you decide who reaches his octet and who doesn't is by the one who has the strongest electronegativity. The one who has the strongest electronegativity will reach its octet. The one who's weaker is going to get screwed. Okay, so who has the stronger electronegativity? Let's go back to that table. Oxygen has a stronger electronegativity than nitrogen, right? Nitrogen is 3.0, oxygen is 3.4. Okay, so who's going to try to reach its octet? Oxygen. Okay, so oxygen is going to reach its octet. Okay, so if we take a look here, there's 2, there's 4, there's 6, there's 8 around oxygen, and then nitrogen gets screwed. It gets what's left over. So it's going to try to get as close to the octet as it can get, but it will never reach it. It'll get to 7. So that's 2, that's 4, that's 6, that's 7 electrons around nitrogen. Okay. So another example is nitrogen dioxide. So 6 times 2 is 12, plus 5, 17, right? So both of the oxygens are going to reach their octet. That's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 7 around nitrogen, right? Because you have an odd number of total valence electrons when you add them all together. Okay, so that's your very first exception. Odd electron. Okay. So the next exception is called hypervalency. Hyper meaning more. Valency. So this basically means that you could have more than 8 around you. Now there's only so many molecules that are able to do this, right? So if we look up the periodic table, I can find it. So all of the elements over here, and it only happens when we're sharing electrons, right? We're sharing electrons. This is when this is going to happen. So these elements over here, group 3, period 3, not group 3, period 3 and beyond, down here, these guys are capable of doing this because what they'll do is they'll use, because they need the orbitals to stick it into, what they'll do, they'll use these guys, which this is the 3D. So they'll use that d orbital to start sticking electrons in, right? So they'll be able to share more if they have to. And they only do it if they have to do it. So if they're forced to do it by something that is really, really strong, like fluorine, fluorine is very strong, so it'll force other molecules to take on and do crazy things, right? And that's only the ones that it can do that to, the ones that it can punk around, are the ones that are in the 3rd period and above. So 3rd, 4th, 5th period, right? The ones that are in the 2nd period, it can't do that to because they're strong. They're a lot stronger than these guys are. These guys aren't as strong. Okay, so it can pump these guys back. Okay, so it can make them take on extra electrons. What was that? Fluorine. Fluorine. So not only, but not the only one. So these guys, it could also happen with oxygen and these. So any of these guys could actually do that to the others, right? So it can force them, but they're capable of doing it. They're able to take on that extra because they have this the D sublevel that they could throw electrons in, right? Available to them. Where these guys don't have that. They don't have that ability because they don't have the D sublevel to throw anything in. Okay. So
because they don't have any
yeah, so no, but they'll force the other guys, the weaker guys, to do it. That's right. Exactly. So they'll make them do it, right? So because they can, yeah. And then also because they're also weaker in electronegativity, those are going to be in the center, right? And so they have them available to do that too. Okay. Good question now. Man, you're good today. You're on fire. El fuego. So these are examples. If you look at it, that's 2, that's 4, that's 6, that's 8, that's 10. Okay. Now, a lot of times when they do this to make it more stable, right? And they'll do it for stability purposes, right? And so the reason that they'll disobey the active rule is if it makes it more stable, okay? Let's see. So our next example is called hypovalency. Okay, so if hyper meaning that you have more greater than the octet, so what does hypo mean? It's going to be less. So beryllium is a metal, but beryllium has a complex. Have you ever met the person that, you know, they're black, but they don't want to accept that they're black or anything like that, or, you know, so you met people that have been like that before, right? You know, that there are certain, you know, there's certain things that they don't want to accept that. Sorry, it's true. Reality, come on now. We're going to be real, right? We're real, right? We're all friends, so we can be real with each other, right? So you're always going to meet people that are going to be, you know, out of character or a little bit different, right? So beryllium is kind of like that. It's a metal, but it doesn't want to accept that it's a metal. So since it doesn't want to accept that it's a metal, it's going to form covalent bonds. But it only wants to have 4 around it. It doesn't want to have, you know, the 8. So it's limited. So it will only have 2 bonds that it can form, 1 on each side. So it's going to have 4 electrons surrounding it. Okay. So, and that is particular when it's with fluorine. It actually forms a covalent bond with fluorine. Even though it has ionic character, it still wants to act like it's not a metal. It's like, nope, I'm not a metal. You know? 2, 4, 6. It only has 6 around it. So boron. No, this is boron now. This is beryllium. Yeah. Yeah. So beryllium only wants to have 4 around it. Boron only wants to have 6 around it. Okay. So those are 2 exceptions. Okay. Okay. So hypovalency is another form of an exception. Yes. It basically means that it has less than 8. It doesn't obey the octet rule. Right? Yeah. Okay. And the last exception is sometimes we get oxygen. You know, when we're talking about per, when we use that per, you get that extra oxygen. So sometimes we don't obey the octet rule because you have that whole extra oxygen to deal with, right? And so, and then so it'll force like sulfur and stuff like that to have 6 around them and stuff. So it kind of falls in that same concept as hypervalency. Okay. You guys are struggling today. Is it a Monday? Yeah. Well, oxygen, no, the center atom would have hypervalency, right? No. Oxygen wouldn't. The center atom, oxygen can't. Yeah. Okay. So on the exam, often there's on the ACS exam, so there's a question that deals with hyper and hypovalency. So, and it's like, which one of these elements can have hypervalency? right? Meaning that they can have more than 8 around them. They'll put oxygen, they'll put fluorine, they'll put nitrogen, and they'll put phosphorus. So which one would it be? It's, what did you say? Why is it phosphorus? That's right, it's in period 3 and below. So anything that is higher than period 3, right? If it's period 4, period 5, or period 6, then those guys could actually form hypervalency. Good job. That's right, because they're weak and they get pushed in the middle, right? And also note, because remember, we also have the D subshell, right? The D starts at 3, right? Okay, so because the D starts at 3, that would be the case. Yes. 3 and above, yeah, period 3 and above. So 3, 4, 5, 6. Well, we're meaning down, you know, because periods get greater when you go down. Yeah. So the number 3, 4, 5, 6. Yeah. So those periods. Okay. Yeah. Oh, sorry, what, 4? 4? You'll get used to it too, because then you'll start looking at, oh yeah, okay, that makes sense. And then you're like, oh yeah, yeah. Okay. Doing pretty good. Now we get to talk about metallic bonds. Metallic bonds are the best bonds ever. We're talking about bling now. Okay. So in the case of metallic bonds, and we did talk about this already. So in the case of metals, what they do is metals will, because they like to get rid of those electrons, they like getting rid of electrons, they will literally drop the electron next to them, right? It'll still be close enough, right? So that water can't get to it and all of that and separate them, but they'll drop it next to them. And so when it does that, it's called delocalizing electrons, right? So the metal literally does this. Drops the electron right next to it. So if the next electron acts like a negative charge, then the metal now is acting like it's a positive charge. So nope, that's not my electron, you know, right? That's just a positive dude, right? So they treat it like it's positive. So you get positive, I mean negative, positive, negative, positive, negative, positive, negative. So this guy is positive, the electron is negative. This guy is positive, the electron is negative. That's its electron that is dropped next to it, right? And acting like it's a whole atom that is positive. Now, since it's so close still, you're not able to disrupt it easily, right? It takes a lot of energy to sit there and disrupt it because it's still playing with that positive and negative charge. So metals are very strong. Most metals are solid at room temperature, right? Solid, right? Solid. So part of the reason is because the electron is still so close to that you can't disrupt it so easily. You have to put a lot of energy in to melt it, right? To separate.
So in the how like color,
Uh-huh.
like the negative going around.
Yeah. It stays together, but because it uses that positive and negative, because remember, it's kind of like ionic, right? Plus, minus, and that's really strong, right? And so as soon as you start heating it up, you start messing, you start fucking with it a little bit. But you have to get enough temperature. It has to be enough energy to sit there and disrupt it. Okay. Yeah. So if it's magnesium is going to lose 2, right? It's going to drop 2 electrons instead of just dropping 1. And so it's going to do exactly the same thing. Okay. So this is called the sea of electrons because the electrons are swirling around it and keeping it together. Okay. Now this kind of works in our favor too because we can form alloys. How many of you guys got jewelry? Anybody got gold? Who got rose gold or is it 24 karat gold? You know, got 24 karat gold, got 18 karat gold, right? So 24 karat gold is pure gold, right? So if you have 14 karat gold, that is a lower percentage of gold. It has gold, it has silver, and it has copper, right? If it's 18 karat gold, it's gold, silver, and copper. Okay, so these form what we call an alloy. Alloys are basically, get there. Alloys are just basically, it's metallic bonds that have mixtures of metals, right? So it's like a metal bond. So that's why we call it metallic bond. So in that case, gold, 18-karat gold, 75% gold, 12.5% silver, 12.5% copper, brass, that's 60 to 95% copper, 5 to 40% zinc. Bronze is going to be 90% copper, 10% tin. Carbon steel is 90%, 99% iron with 0.2 to 1.5% carbon. Pewter, 91% tin, 7.5% aluminium, 1.5% copper. Stainless steel, and I want to make a point of this, right? So if we just have iron is going to rust. Stainless steel doesn't rust, but the reason why it doesn't rust is because you put other metals in it. You put the chromium and you put in nickel, right? And that keeps it from rusting. Okay. So steel, yes, steel would rust. If it's just iron steel, 100% iron, it's going to rust. So over time, so you guys heard of the bridge in what was it, Michigan, that fell down, right? Right, it was like right before the president got there. He was like visiting this town, and the bridge broke down. Like it was like a week before or something like that. Okay, so that's an example. They used to use pure iron for building, but over time it rusts, right, and it gets weak. Okay, but if you put, yeah, because oxidation, exactly. But if you put stainless steel, it doesn't oxidize, right? It was significantly more expensive because you're putting in expensive metals. Yeah, you're mixing those metals, right? So, and they form beautiful alloys, yes. Yeah, you just said that, yes. Oxidation, that's correct. Yeah. Okay, sterling silver, 92.5% silver, 7.5% copper. No. But it can make your neck, green, right? It actually it starts reacting with some of the components in your sweat. So yes. Yes, stainless steel after a while, because the iron actually starts interacting with other things, but it won't turn brown as frequently as steel alone. So because it's not being oxidized. That's right. Yeah. Yeah. Exactly. And it's the more iron that's in it, the higher percentage iron it is, the more brown it's going to turn. So if you get more and more chromium, then that's going to keep that from happening. Okay. But so then that's why if you buy the cheap brand, they cheated you out of some of the metal. So okay. Are there any questions? Okay, so we're actually going to stop here today, if that's okay with you guys. Yeah.